since 1970 and was with them all the way through 2005, 2006, where he was managing the geophysical component of Placerdome's leading edge exploration program to see, I get lost in this. There's so much here. I'm trying to paraphrase because it's like half a page. I'm just skipping ahead here. So we'll just skip to the last part. He is the inventor of the patented ocean floor geophysics submarine electromagnetic system and has been part of that team that has developed the magnetometer system that provides automatic and highly accurate heading compensated data mapping on AUVs and ROVs that have been degassed or specifically prepared as magnetometer geophysics platforms. Whew. All right. I know, after this. Let me introduce Peter. Thank you.
So I'm going to talk about using CSEM for gas hydrate exploration. It's a new method that's being developed called the VULCAN system, where instead of using seafloor nodes, you're using a towed system that trails behind the transmitting dipole. So the general content will be a review of gas hydrates. I want to give an example from the Greenland Sea of a gas hydrate example, some exploration models for gas hydrate deposits, motivation for doing CSEM, description of the system, and then model study. And I regret that I can't actually show you any data. Most of the work, almost all the work we've done has been done in Japan for the Japanese government, and they have been quite tight about releasing any data. Recently, they've actually started to put out a few press releases, and they've had some public conferences, but there's actually very little data that's available in any kind of journal that I can show you. So the economic drivers, why are gas hydrates important? Well, Japan, it requires energy, and so they're trying to enable commercial use of gas hydrate resources, which they have in Japan, and they'd like to see that by fiscal 2018. That's perhaps a little bit early, but they actually have built a ship, and they have had test production from gas hydrates in Japan. The really interesting thing is the estimate of the world resource estimates for gas hydrates, and the present undiscovered conventional natural gas reserves are something on the order of 13 times 10 to the third trillion cubic feet. The global gas hydrate resources are really not known, but they're much, much larger. So it's something on the order of 100 times 10 to the third to 300 times 10 to the sixth trillion cubic feet. So it doesn't matter really what the number is. The point is that gas hydrates have the potential to be a very significant energy source in the future, and perhaps to supplant the hydrocarbon resources that we depend on now. And countries that are very interested in it are hydrocarbon consumers who don't have their own and who require energy for strategic reasons. Examples are Japan, Korea, and interestingly enough, India. So this is just a news release that shows that they did produce gas hydrates. These were produced from the what we'll call the conventional gas hydrate style of deposition, which is just above the bottom simulating reflector at the base of the gas hydrate stability zone. And here's the seismic response of these gas hydrates that they drilled into. Recently it's been recognized that there's another important style of gas hydrate concentration. These gas hydrate mounds on the seafloor have been known for years, but they were never thought to be very large. And recently it's been shown that these are kind of little pimples of much larger bodies existing close to the seafloor, which might be a really significant and easily accessible source of concentrated gas hydrates. So if you look at gas hydrates, there's a stability zone in the ocean. Basically, as the ocean gets deeper, it gets colder, and then when you hit the seafloor, you get the geothermal gradient, and then there's pressure determined here as well. But what happens is from the seafloor, generally deep seafloor, down to the base of the gas hydrate stability zone is something on the order of 150 to say 300 meters in different parts of the world. And you recognize this BSR, bottom simulating reflector, because what happens is the polarity of up here you have solids, down here you have liquids. So if you have, or gas, so you get a polarity reversal and you get a non-conforming seismic reflector that marks the base of the gas hydrate stability zone, the BSR, bottom simulating reflector. This is just a map of where the hydrate stability zone exists in the world and how thick it is, and you can see that there's gas hydrates all over the world. This doesn't necessarily mean that these are all economically exploitable, but it means that if you're going to look for gas hydrates, you want to look in these regions. And this is a seismic image, high precision 3D seismic survey that was done in the Greenland Sea. They have mapped a large number of gas chimneys and pockmarks on the seafloor, and these are often associated with gas hydrate close to the seafloor, that is well above the gas hydrate stability zone. And they're generally linear, and they occur in groups. So here's just the bathymetry. You can see these pockmarks. These are depressions, and that's where the seafloor has eroded. And I mean, one of the ideas, it sounds a bit sort of cataclysmic, but you get a pockmark like this. If the seafloor has become filled with gas hydrates, it actually has positive buoyancy, and so it break loose from the seafloor, float up, and dissolve itself like a massive Alka-Seltzer. And you know, it's being proposed that this is the reason that ships have been lost in the Bermuda Triangle, because they've been sunk in a boiling sea of gas hydrates or methane. I like to use the idea of a North Systems deposit model. This style of model is after Craig Hart in DRU. And when you talk about a deposit, you try to put it into a description that describes in a generic way the controls for the deposition of that deposit. And gas hydrates are or can be thought of as being very similar to a mineral deposit. You have fluid flow coming in. You have the deposition at some kind of seal or geochemical gradient, which in this case would be the seafloor. You need to have host lithology. You can think of a gas hydrate deposit in these terms. So here's an exploration model for a gas hydrate deposit, and you have two styles. You've got the gas down below, and when the gas comes up through the base of the stability zone, you get a large low-grade gas hydrate deposit. This is generally where people expect to find gas hydrates, although they're stable in this whole zone. But if you have a little bit of a structural high and a fault, okay, you get gases coming up here. This is where the pockmark occurs, and this is actually where you can get the high-grade gas hydrate deposit. And there's where the mound is, just a little bit showing, maybe on the side of the pockmark or somewhere close by. Nobody really knew how big these deposits were, and what the concentration in them was. So, here's an example of the gas hydrate, the things that you can use to look for it. So you need to be within the gas hydrate stability zone. One of the controls is the base of the gas hydrate stability zone. You also get a tremendous gradient at the seafloor. You get methane coming up the faults, and actually you get clam beds around the gas hydrates on the seafloor, which you can see with sonar. You get outcrops of the gas hydrates. The fluid pathway, you need a fault, probably a structural high to bring the gas to it, and pockmarks are a sign of that. You can see some things in the seismic velocity, but it's not very good. Gas hydrate's resistive, so electrical surveys will look for it, and if you find a mound on the seafloor, you can break a piece off with an ROV. So there's lots of ways to look for it, and the trick is to find an efficient way to organize yourself in this to map out the gas hydrates. So just to go back to this, seismic is not very good. 15% of the BSRs that have been recognized when they drill them is very little gas hydrate. Okay, there's another statistic that about 40% of the gas hydrates don't have a strong BSR when they drill and encounter the gas hydrates. But if you look at the drilling results, here's a section of gas hydrates, and this is 100 ohm meters. Okay, and so it's much more resistive than the seafloor, which is probably 1 or ½ ohm meter. So it's clearly a good target for a resistivity system. And in fact, this is just a published log. You can get resistivities that are much higher than this, and the theoretical limits for 100% saturation are about 2,000 ohm meters in an environment where the sea is 0.3 ohm meters and the seafloor is 1/2. So this is the Scripps CSEM VULCAN system. And what you do is you have the ship, you power system on it, you're transmitting through a transmitter here, which is transmitting an electric waveform, okay, and you have a dipole down here that's transmitting into the seawater. This can be 50 to 100 meters, it can be larger, and you can typically transmit 100 to 400 amperes. So it's a fairly high-powered system. Voltages are not very high, but you still want to be pretty careful when you're transmitting with this on deck. So this is where the current is being transmitted into the seawater. And then these are the receivers. And these are interesting that you don't have a current received dipole. You do, but it's on this little receiver. The electric field is being measured by a 2-meter dipole here, a stiff 2-meter dipole. And the cross-track fields are being measured on electrodes at the top ends of these fins, and they're 1 meters. So we have an instrument which is measuring the instantaneous voltage gradient, 2-meter long E-field probe in the seawater. Otherwise, you can more or less think of this as an IP system. You know, it's transmitting a current and you're receiving voltages. And the other thing we have is GPS, well, a very accurate clock here and very accurate clocks in these. As this waveform is being transmitted and it contains different frequencies, those frequencies roll out in phase so that you get a phase delay here. And the response of the sea is pretty constant. You know the conductivity of the seawater, you know the depth and geometry, and the differences in the measurements are due to the resistivity of the seafloor. So this is a picture on a ship. There's the cable going down. That's the transmitter. We're about to lower it into the water. The receivers are floating out behind here, and the last receiver is 500 meters behind us. Those are the two electrodes for the transmit antenna. This van here has got our power supplies in it, spare parts, and then we had a control van that we had a crew running the whole system. So this is an example of the waveform. It's called a D waveform, and it on a 1 hertz primary harmonic or primary frequency. You have harmonics at 3, 5, 7, 9, 11, 13 onwards. But you can see that with this waveform, it's designed to actually have considerable power in the harmonics, and we have power at 3, 7, and 13 hertz, particularly on a 1 hertz base waveform. This is the receiver, just to show you what it looks like. Oh, there's a non-polarizing electrode in there, quite a carefully built one. And there's one there, there's one there, there's one there, one there, and one there. So that's one dipole, that's one dipole, and that's one dipole. And inside there's a very, very accurate low power recording voltmeter. And also we're recording the depth of the system very accurately, and time. We have a very accurate crystal clock. And so we put this thing in the water and we will operate for, say, 7 days. It's an act of faith because you can't see your data. You just put the thing in the water and let it run, and then you bring it back to see if you have data. So we have now the ability to bring some health data back, and that gives us confidence that we are actually recording data. So what are the important things here when we're operating? Well, navigation is very, very important because we need to combine the results, and we're towing something half a kilometer to a kilometer behind us in 1,300 meters of water. We want to know exactly where the transmitter and all the receivers were, and we also want to know line to line how the various data sets, how the data combines together. So we have a USBL system on the head and the tail of the array. That's a sonar distance and range, direction and range system, and it gives us an accurate position. And then we have pressure sensors which tell us how the array is sitting in the water. The helmsman job on the ship is not to keep the ship online, it's to keep the transmitter online. And that takes a little bit of readjustment for the average helmsman. But we've got them now so that they're trained to that, and we put a display up that they're watching where the transmitter is and not where the ship is. Data quality control is really important. We review it on the ship, and we produce preliminary apparent resistivity sections, and then we prepare the data for 2D and 3D inversion, and it's sent to shore for analysis. And for the work that we did, that work was managed by CGI and Mirror Geoscience, and we produced 3D models of the data. So this is a hypothetical theoretical model, and I'm showing it to you as an allegory for the work that we did, because I can't show you the work we did. So I've taken a seismic cube from the Greenland Sea, and I've modeled the seafloor is 75 meters below the seafloor using gas hydrate properties of 220 and 200 ohm meters, and surrounding sediments of 1 ohm meter, seawater of 0.33, and then I've calculated a couple of examples. So here's the detailed sea bottom reflectance showing one of these chimneys. And so there's the outline in the seismic section. So we built a seafloor model. This is the base of the gas hydrate stability zone. This is the seafloor sediments. And here's some near surface gas hydrate or a gas chimney that we put into the model. And so just taking a section through it, that's what the chimney looks like. It's important to note here that in this numerical example, it's only 3 or 4 cells across. Okay, so the first one is this gas chimney. It's 2 ohm meters. Okay, sediments, seawater, base of the gas hydrate stability zone. So we model a gas chimney of 2 ohm meters, and then we inverted it, and actually we get the shape of the chimney very well. But it's not a very big difference between the resistivity of the 2 ohm meter chimney and the sediments. So here I put a gas hydrate cap on this gas chimney, and it's 3 cells thick. It's 20 ohm meters, not very much gas hydrate, but again, when you do the calculation, here's the model, and then I've just shown where the resistive part of it is, and it gets it, but it's starting to not gripping the resistivity very well, and that's because it's such a small body. So you can see in the center of it, it's got probably 20 ohm meters in the center, but it has to have some smoothness going from the surrounding sediments to the resistive body. And so then the next case, I put a 200 ohm meter body on here, and same thing happens. You identify this resistive body very, very well with the notional CSEM system, the VULCAN system, but you don't get the resistivity particularly well. What happens if this body gets bigger is that you do get the resistivity. at least you get much higher values. Whether we're going to get 1,000 ohm meters, I don't know, but you can get 200 and 300 fairly well. So just to show you, there was quite a bit of discussion as to whether these gas hydrate bodies really did exist. And in March 2015, we did an orientation cruise off San Diego with the CSEM system to test it before we took it to Japan. We went over a gas hydrate vent. This was a known gas hydrate occurrence, but this resistive body underneath it was not known. And the resistivity of that is in the order of 100 ohm meters or greater. And this was a very pleasant surprise from this data. When you look at this, there's no seafloor nodes here. These are the positions of the VULCAN system as it was towed across. And this is the 2D inversion result done using MARI 2D, which is public domain code available from Scripps. And this work was done by Constable and Canberg and Wiedemeyer, so it's been written up. And just this week, the Japanese have released a press release, and they have said that these shallow gas deposits are an important resource in the Japanese gas hydrates deposits. This is extracted from the press release today, and they say that they used, I'm not sure what LED method is. Seabed drilling was conducted, and this I think is logging while drilling. That they had they made physical property measurements and looked at and pressure coring to take samples from this this zone. And if you look at the scale of this, that's 200 meters. So this is something on the order of 250 by 400 or 500 meters. Then they used electric resistance underneath the seabed collected by marine-controlled source electromagnetic method. So that's the VULCAN CSEM. And then using those results, they estimated the resource for this particular body at over 600 million cubic meters of methane hydrates. So this was a real pleasure to see released, and it's very good news to know that the CSEM data was used in this estimation of the potential resource. So just to summarize, the VULCAN system is suitable for characterizing shallow gas hydrate deposits. It's complementary to other geophysical and geological methods. It's the only method that has the promise of assessing both the volume and the concentration of gas hydrate, and it fits well into a resource definition program. And the CSEM equipment and software works well, and it provides a tested exploration method with low risk. We know how to do the surveys. There are robust 2D and 3D inversion codes available for use, and it's cheaper than drilling. So large areas identified as prospective can be tested for priority targets, and then the best targets can be drilled, and you'll have confidence that you have drilled the best targets. So to me, it's been a very interesting ride, and I'm very pleased to show you these results. I'm sorry I can't show you more. Thank you.
Questions for Peter?
Can you explain how they intend to produce the hydrate? Extract the gas?
Well, the gas that sits just above the BSR, the intention was to drill it and then to warm it and to use kind of a normal oil field style extraction process. I don't believe they can do that for the material that's close to the seafloor. And I think, and this is an arm wave because it's not my strength, but I think they're going to mine it. And
Encapsulated in paper?
well, if you mine it and bring it up, it'll be foaming.
Yeah,
but you could have a production platform and you could capture that, I'm sure.
Was that press release in Japanese economic development zone, or was it out in the international waters?
No, all of their resources that they're investigating are in their economic zone. They typically, there are resources outside, but they have concentrated on their own gas hydrate resources.
Do you get any sense of false positives, like other things that could be causing the resistance?
Well, you always have to be careful, and one of the thoughts was that, we might be looking at calcareous sediments, but these are pretty strong anomalies. And if you see them associated with a methane vent and pockmarks, I think you probably got pretty high odds of it being a...
So you have some kind of radar or sonar on the front as well, taking imagery as well?
Generally speaking, the cheapest things to do are bathymetry, and that'll be done in advance to pick out the areas where the pockmarks are that we're going to do the CSEM on.
Was there the volume estimate that they gave you, was that based on a couple of drill holes and your inversion, or what was it based on?
I don't know, but my reading of the press release is yes, that they haven't outlined, from their drilling, they haven't outlined the limits of the body. So I'm guessing that they have an estimate of grade in the body, and they're using the electrical results to estimate its size.
Have you played around with any sensitivity analysis to give you an idea of the depth penetration of the array that you're using?
Yes, but not a lot. The targets were expected to be above the BSR, and we knew that the BSR was in the order of 150 to 200 meters. So we did check that we were sensitive. If you want to see deeper, you need to extend the array, and if you do that, you have trouble navigating the tail of it. So for operational reasons, we were using a 500-meter array so that we would know where it was. And everything we did was very incremental. We didn't want to go out and find that we'd made a mistake. And, yeah.
What do you do during the week when it's acquiring data?
Well, the first week you worry. The second week you're processing what you acquired the week before.
Any other questions?